Welcome back to our second lecture of the morning, the first lecture by Geoff Peningto, who will tell us something about black holes and entanglement.
I don't know. We'll see.
Something fun, I'm sure.
Cool. Okay, thanks Brian. Thanks for inviting me to lecture. So yeah, my plan for today is going to be very old-fashioned and you know, all stuff at least 10 years old. A lot of it's going to be stuff from the 1970s, basically about the black hole information problem. Because at the end of the day, the reason we all care about sort of quantum information with quantum gravity, if you go back before ADS-CFT was a thing and so on, is the black hole information problem. That was the first big hint that information theoretic aspects of quantum gravity are really doing something interesting and non-trivial. So then tomorrow, we'll switch tracks and we'll talk about ADS-CFT, so a bit more up to date, particularly about reattacking Nagy formula, its generalizations, deriving it, and so on. And then finally on Wednesday, we'll get to exciting modern stuff and talk about how these things come together, and we can use those tools that were developed for ADS-CFT to derive the page curve and other interesting facts about evaporating black holes. Okay, and let's just start with something very simple. The vacuum of a quantum field theory in 1 + 1 dimensional Minkowski space. So this is a state that we can construct using a Euclidean path integral by having an infinite path integral in Euclidean time, some boundary conditions, phi of x, and then this gives us a number for any boundary field configuration phi of x, and that describes the wave functional of the vacuum state. Okay? Reason this just works is because what is this computing for us? It's an inner product of phi of x e to the minus tau times h times some initial conditions down here, whatever they might be. Let's call them phi prime of x. Something suitably generic. And in the limit where tau goes to infinity, this is just going to project us onto the vacuum state, kill off anything else. Okay, so let's just erase this because it doesn't really exist. It's off at infinity. And so this just describes the Minkowski vacuum. Okay, so we'd like to understand what the state looks like in more detail. In particular, we'd like to understand its density matrix on x greater than or equal to 0. Okay, so how do we construct a density matrix? Well, we just take a ket and a bra, and then we do a partial trace over everything that we don't want. Okay, so the ket we just described here. The bra we can construct with another, in exactly the same way. It's another Euclidean path integral, where I've drawn it upside down because it's a bra rather than a ket, but it's just the same Euclidean path integral with some boundary conditions here. And then to do this partial trace, all we do is we take the fields we don't care about, the ones with x less than or equal to 0, and we're just going to integrate over, force them to be equal to each other on top and bottom, and integrate over all the possible configurations. Okay, what does that do? Well, it's just equivalent to, you know, that's just what we do ordinarily in a path integral. So we've effectively just erased these boundaries here, and we now have a path integral on the full plane, except with a cut here, where we have, you know, some configuration phi prime of x here, and phi of x here, x greater than 0, and that describes the density matrix in terms of these field configurations of the state on x greater than 0. Okay, so then we can do this classic beautiful trick, which is to look at this same path integral and interpret it in a different way. So rather than thinking of evolution going from bottom upwards as using the Euclidean Hamiltonian h, we instead think about the path integral as rotating us from here around in a circle and to here. So we think about what the path integral is doing from here to here, and then to here, so on, break it into little pieces. Each of those little pieces is just a Euclidean rotation, and so we conclude that this density matrix is just e to the minus 2 pi times the generator of Euclidean rotations. Okay? In Lorentzian signature, this is the generator of Bose. Great. So that is, of course, the famous derivation of the Unruh effect, that the Minkowski vacuum looks thermal to a point of view of an observer whose world line describes the action of a boost, i.e. constant acceleration. But it's a bit abstract. It's, we don't really know what this density matrix actually looks like in practice. And we'll need that because we want to get Hawking radiation eventually. So let's be slightly less abstract and consider the case of a massless free field. Okay? So exactly the same setup, but we now know what our QFT is. So how would we solve, how do we understand free field theories? Well, one way to do it is to look for a set of modes, solutions of the classical Quine-Gordon equation that have definite energy, i.e. their solutions, d by dt squared minus d by dx squared, some function f equals 0, such that the time dependence of f just looks like e to the minus I omega t, okay, for some omega. What are these in this case? Just e to the I kx minus modulus kt, okay? Just plane wave solutions. And the way free field theory works is that when we expand our field operators in terms of these modes, then the amplitudes of each of those modes, when we quantize, get promoted to things that become creation and annihilation operators. And for each mode, we get a simple harmonic oscillator. Okay? So we'd like to do this same thing, but now, rather than modes of definite h, we want modes of definite j, because those are the modes that are gonna look nice, could be diagonal in terms of this density matrix rho. Okay? So what are those modes? Well, they're called Rindler modes, and to find them, it's helpful to change coordinates. Pretty simple coordinate transformation, what are called Rindler coordinates, rho and tau. So what do these coordinates look like? Let me draw down here. So we have Minkowski space with a light cone going out from the origin, and let's get a couple of colors here. So these coordinates just describe the Rindler patch, so where x is greater than the modulus of t. And the lines of constant tau are just lines of constant boost angle. So say this is tau equals 0, this is tau equals 1, this is tau equals minus 1, and so on. And meanwhile, the lines of constant rho are just hyperboloids, so they describe an accelerating observer, the action of a point under this boost symmetry. Okay? So in terms of these coordinates, j is just equal to minus I d tau, in exactly the same way that the h is equal to minus I dt, it just generates shifts of tau. And so if we can write the Klein-Gordon equation in terms of these rho and tau, then we'll be able to identify modes of constant tau, okay, of constant j. Okay? So it turns out, this is an exercise, it's a very simple one. If you rewrite this equation in terms of rho and tau, you get something that looks like an e to the 2 rho out the front, and then you get a d by d tau squared minus d by d rho squared. So, if we ignore this, we can divide through by that factor without changing the left or right-hand side of the equation. And the relevant solutions, which are called G maybe, are just plane waves in Rindler coordinates. Okay, these are known as Rindler modes. So they look like e to the ik rho minus modulus of k tau for all positive and negative values of k. One describes right moving modes, one describes left moving modes. And they have a boost energy that's just given by the modulus of k. Okay? So, if we go back over here, once we promote the amplitudes of these modes, creation and annihilation operators, and the usual story you heard somewhere at the beginning of QFT class, you end up with the density matrix being a tensor product over modes of thermal density matrix on a simple harmonic oscillator, e to the minus 2 pi kn, of nn, where n is telling you the occupation number of the mode. Okay? So I want to emphasize that it was really something special about a massless free field that meant the Klein-Gordon equation stayed unchanged when we went to Rindler modes. In fact, it's because the massless free scalar field is secretly conformal, and we were secretly doing conformal transformation. In particular, if you imagine I did instead the massive Klein-Gordon equation here, then I get an m squared term here. But because I have this e to the 2 rho out the front, here I would get an m squared e to the, I think this should be a minus 2 rho, e to the 2 rho. Okay, so this gives us a position-dependent potential that scales exponentially with rho. Okay, so if we now look at what the Rindler modes would look like, they're no longer plane waves. Instead, we have something that looks like v of rho is growing exponentially. And if our mode has energy k, it's going to start being a plane wave over here, but then it's going to become longer and longer oscillations. Eventually, the energy of the mode is going to become less than v, and it's just going to exponentially die away. Okay? So for modes of order 1, which are the ones, k equals order 1, which are the ones that are actually thermally excited, then you'll find that they're localized within a distance 1 over m of the horizon. This is telling you that in a massive quantum field theory, then entanglement is localized to differences that are order 1 over the mass. Okay. Great. So now let's go over to black holes. Okay, so the amazing thing about this computation is that even though it relied so heavily on the symmetries of the vacuum state and so on, if I look at small enough distances, if I really zoom in on a tiny point, then any state looks like the vacuum state. So actually this very special calculation that relied on these special properties of the vacuum is actually telling us something universal about all states of quantum field theories when we zoom in on a small enough region. So let's look at the case of a black hole. Schwarzschild black hole, maximally extended, looks something like this. We have a metric that, if I can remember my GR, looks like 1 minus RS of R dt squared plus, I guess, the inverse of this, dr squared plus r squared d omega squared. Okay. And far from the black hole, shifts d by dt just look like in Minkowski space, they're just shifts of global time. Okay? On the other hand, if we're in the very near horizon region, then lines of constant t translate forwards on the right, backwards on the left. So very close to the horizon, they look like boost time. In fact, the relationship between the boost time that we had before and t is t equals tau over 2rs. You can check this explicitly. It's an easy exercise. So if our state is going to look smooth at the horizon, then in the very near horizon region, modes localized that have constant Schwarzschild energy T should be thermally excited with temperature beta, inverse temperature beta equals 1 over 4 pi s. Whoops. So before we had 1 over 2 pi. Now we have an extra factor of 2rs converting between Schwarzschild time and boost time. Okay? From there, we want to conclude that if we go to late enough times, then you'll see Hawking radiation coming out from the black hole that is far from the black hole and has the same thermal energy. This is actually, go ahead.
Dimensionally, I think that looks a little weird.
Sorry, yeah. Good. Beta T, you know, the same thing. Working in coordinates where, working units where beta equals 1, so both the sides were equal to 1. Okay. So this is actually somewhat subtle for a general interacting theory. I don't know of any good derivation of it. But for free theories, then it works. It's pretty easy to show. whereby pretty easy, I mean much too annoying, complicated for me to show in detail in this talk, but I'll at least give you a heuristic, quick story of it. So the trick is that this near the horizon, then little t is proportional to tau, but the coordinate r does not look anything like the in the coordinate row we had before. Okay, so we're going to switch to a coordinate row that looks much more like that. It's called the tortoise coordinate, and it's just equal to r plus log r over rs minus 1. Okay, you can check the very close to the horizon row is just exactly the same as the row we had here. If we now take the classical solutions to the Klein coordinate equation on the Schwarzschild background, then in terms of t and rho, we end up with something up to factors out the front that I'm not going to try and get right, minus d by d rho squared, minus some position-dependent potential rho that will depend on the angular momentum of the mode equals 0. Okay? And the important point is that as rho goes to minus infinity, i.e. very close to the horizon, then this just becomes like Windler space and v goes to 0. And similarly, when rho goes to plus infinity, then it just becomes like Minkowski space, and v again goes to 0. So our solutions to the Klein-Gordon equation have rho and we have v, look like a particle with some positive potential bump that then dies away at plus and minus infinity. Okay? To sketch the rest of the story, we can have wave packets here that are localized, you have very close to constant k, and are localized well to the left of this bump. That means they're very close to the horizon. The bump is roughly at r minus rs equals order rs. Okay, so they're much closer to the horizon than the bump is. And from our argument that locally it has to look like the Windler vacuum, thermal state, it's the Minkowski vacuum, then these modes should be thermally excited. Okay? But then, these modes move, they'll evolve forwards in time, and what happens is that they hit this bump, something complicated happens, we won't try to understand. Then if we keep going long enough, the sort of only two things they can end up as, because everything's linear, this is just Klein-Gordon equation with some potential, is either some part that has got reflected back into the black hole, and again looks like a Windler mode, this time a left-moving one, plus some part that makes it over the bump and makes it out to infinity. And now that's a plane wave in rho, but that just means it's a Minkowski's plane wave, so it's a real thermal radiation. Okay, so this part that makes it out is the Hawking radiation. The probability that makes it out is what's called the gray body factor. And in general, it will only be small. It will only be significant for modes that have an angular momentum that's order 1. So the height of this potential is order L squared. Okay, and that means the probability of it making through is exponentially small with large angular momentum. This is a very high potential, and the energy is still order 1 if it's going to be thermally excited. And so the Hawking radiation gets dominated by low angular momentum modes. People sometimes phrase this as Hawking radiation being, well, by people I mean, I sometimes phrase this, I don't know if I've ever heard anyone else phrase it that way. Hawking radiation is a fundamentally two-dimensional problem because it's dominated by the S wave and a few other modes with order 1 angular momentum. Okay, so great. That's the most technical part of the talk in many ways. The question is, what do we do with this? We've concluded that black holes radiate energy in a way that looks thermal. There's these gray body factors in there, but they have a very obvious thermodynamic explanation, which is just that if I send in some ingoing wave over here, has some probability of being reflected off this bump. Okay, so these just telling you that there's a radiation coefficient that is exactly equal to the absorption coefficient. That's a standard statement in thermodynamics that we're seeing that in black holes. So all of this is to say that black holes smell like a thermodynamic object, right? everything about their behavior, at least that we've seen so far, is exactly the sort of thing we'd expect if they were radiating a temperature, because they had an entropy E that depends on, an entropy S that depends on the energy E. Okay? That's how we get a temperature, thermal radiation, and so on in thermodynamics, and we can plausibly guess that that's what's happening here. Okay? So if we write this equation, use our known formulas for the energy and the entropy, for the energy and the temperature, we have T is 1 over 4 pi Rs. We have dE. E is equal to the mass of the black hole, which I believe is Rs over 2G. So this is dRs over 2G. Quick rearranging gives us ds equals 2 pi Rs dRs equals dA horizon over 4G. Okay, so if this temperature is coming from thermodynamics, could be it doesn't, you know, that's a reasonable hypothesis that I don't think is true, and I don't think anyone thinks it's true. Oh, almost anyone thinks it's true. But if it does, then we should have that the derivative, small changes in S from changes in energy are equal to small changes in the horizon area. I've only shown this for short shell black hole, but it's actually far more general. It's a completely general argument. And so we'd like to be able to integrate this, say that at very low energies the entropy is relatively small, and conclude that S equals A horizon over 4G. This has recently got called the central dogma of black hole physics, that this is really true with S here being a genuinely statistical entropy, i.e. heuristically, you know, this is the number of qubits up to maybe a log 2 factor. The number of qubits needed to describe the Hilbert space of all possible microstates of the black hole. Okay. Great. Yep.
So this only tells us about ds. What stops me from adding some S0 that I claim to be
Nothing.
infinity, for example? Okay.
Yeah.
Cool.
It's an entirely, so you know that one of the big assumptions in you know, getting from here to here is that you could have a large S0 term. So say in an example where we can very concrete in like JT gravity, okay, then you know there is an S0 term that we think of as coming from a topological term in the action. You can compute that if you do Euclidean gravity, but that involves assuming how Euclidean gravity works and some magic. So yeah, that's you know, that would be the answer, that they're remnants, right? Or this one answer is that S is always infinite, even at zero energy. It's a bit problematic because then you have infinitely many states that have roughly Planck scale amount of energy. So you know, have fun making a consistent theory of that, but yeah, there's nothing that rules that out from the argument so far. Okay. So great, everything looks wonderful. It's all consistent until, of course, we run into the information problem. Okay. So we just argued. I should have said, by the way, here I was. So here I was assuming that we have a two-sided black hole that is non-singular around this whole region here, and so it looks like the vacuum on it. So that meant I could have made exactly the same argument, but going backwards in time instead of forwards in time, and I would have seen Hawking radiation coming out from the white hole horizon as well. Okay? Obviously, that doesn't happen in reality because our black hole is formed from collapse, so this whole region is totally fictitious, and instead there'll be some infalling shell way down here that we're not worrying about the details of, and then before that there'll be Minkowski space. Okay? And so what that means is if we look more carefully at the state of the Rindler fields, we'll find that right moving modes here entangle with right moving modes here. Okay, so those are real modes that in the interior of the black hole, they actually exist. Left-moving modes, on the other hand, here entangle with left-moving modes down here. Those are completely fictitious. They're not actually in the physical part of the space-time for a black hole formed from collapse. So that's why we don't magically have white hole radiation coming out from black hole before it's formed. Okay. So we have a black hole, and we have some radiation going out. And that radiation is in a mixed state. Except, of course, we know that quantum mechanics evolves according to the Schrödinger equation. So if we have a state at time t equals 0 that's pure, then it evolves e to the minus iht, and we end up with some pure state. Okay, so we have a problem because the Hawking radiation is mixed and it's meant to be pure, right? Somebody complain about how that's not right. Right, if we have a few qubits of Hawking radiation coming out here, there is absolutely nothing wrong with it being in a mixed state. That happens all the time. That's called quantum entanglement, okay? So the reason this radiation is in a mixed state is because it's in something in the interior here. Yep. Yeah.
So what was the conclusion of the statement that you made above that? You've got these right-moving modes. They're entangled, so inside, like,
yep,
on either side of the horizon. And then you've got these left-moving modes, which are entangled to some fictitious stuff. So
yeah, the point is they don't have to be entangled with the fictitious stuff. They need to be entangled with the fictitious. If the fictitious stuff was real, then we would want to have a smooth state here with no sort of shock, infinite temperature shock on the white hole horizon. And to be able to have that, to have a finite energy state across this whole thing, then they would need to be entangled in a thermal state with stuff down here. But we just don't have that. We don't have, in reality, these modes are cut off at some, very slightly above the horizon here. And there is some shock coming in. It's like an infalling shell of matter, and then behind that we have Minkowski space.
Okay.
So there's just no reason that they need to be in that thermal state at all.
Okay, so just to be clear, so in this like double picture, we get this nice sort of potential thing, but like the more realistic thing, if we sort of somehow mod it out or something, we're going to get some other effective potential, and it's going to be the quantum mechanics of that thing, in some sense.
So the point is we have a part of this space-time, but not all of it. We have the part that starts very slightly up and to the right of this horizon onwards, okay? And we need the state of the quantum fields to be non-singular on that whole space-time, the whole physical part of the space-time. On that physical part of the space-time, we have modes here and we have modes here, Rindler modes, and they need to entangle with one another, otherwise you would have an infinite energy shock on here. That's called the firewall in firewall arguments. But there is no, the hypothetical infinite dimensional shock that would be on the right whole horizon just isn't in the physical space-time. Like if we'd been more careful and used something like a Bijah space-time where we can actually see the collapse, then that part just wouldn't have been present, and so we can have a non-singular state on the whole space-time even without these modes being entangled with them. And in fact, that's what you get for a black hole form.
All right, thank you.
Okay, great. Okay, so schematically, these modes are entangled with stuff in the interior, and we'd like to say that the interior of the black hole, if we believe in this central dogma, is described by some state in this Hilbert space of A over 4G qubits. So schematically, we just have a state, psi t, looks like a sum over I, ket I of this radiation mode out near infinity, tensor some state psi I of all this A over 4G qubits that has this interior quanta in the state I. Okay, that would just be some state of all those qubits. We don't know how this sort of simple semi-classical description is related to the microscopic description, but there should be some way. Okay, so that's totally fine, except for the fact that the black hole's not done evaporating, and so it's gonna keep producing more radiation. And if we look at Hawking radiation that's separated by much more than thermal time, then it basically is uncorrelated with the early radiation. That's the statement of thermal physics. It's local correlations on scales of order of the thermal scale. Okay, so roughly, we get another quanta out. Now we have I and we also have J. And now this state of these qubits needs to describe the fact that there's an interior partner here in state I and one here in state J. Let's call it psi ij. And then another mode comes out up here, and so on and so on. And all the while, this entropy SR of these modes is just basically linearly increasing. Okay? It's going up with time. It's not actually quite linearly increasing because the temperature of the black hole will change as it evaporates and gets smaller, but it's getting bigger and bigger and bigger. And meanwhile, black hole's evaporating, so the horizon area is getting linearly smaller with time. Follows that at some point, we must have this thing become bigger than this thing. That is called the page time. When Hawking's calculation of S of R, which I'll call S-rad to distinguish Hawking's calculation from any other calculation we might do, is equal to the area of the horizon over 4G. This happens a little bit before the black hole has half evaporated, a little bit over half its area, because the rate at which this is increasing is actually slightly bigger than the rate that this is decreasing. So at some point we hit that point, and then we're in trouble, because if we believe this is all that's happening, we have some globally pure state of the radiation is entangled with some degrees of freedom in the black hole, then we must have SR equal to SB, because that's how entanglement entropy works. But SB is less than or equal to A horizon over 4G, because the entropy of a qubit is at most 1, right? It's at most one qubit. The maximally mixed state would have entropy A horizon over 4G. Okay, but of course, we just claimed that after this point, this is supposed to be bigger than this. It doesn't take Stephen Hawking to recognize once you have that statement that this is a bit problematic. We have a contradiction here. So the nice thing about phrasing it this way is it makes it obvious what the problem here is, and it's a pretty simple problem. It's that we want this system B that's supposed to consist of A horizon over 4G number of qubits to describe more than A horizon over 4G interior quanta over Hawking mode. Okay? And there's just, there's no way for that to do that with them all being independent states. It's just a state counting argument. So, one conclusion we can make here is exactly that maybe S isn't A horizon over 4G. Maybe there's actually a infinite shift between the two or something that means we never run into a problem. The other thing we could conclude is just that somehow Hawking's calculation has to go wrong. Okay? And in fact, there's a pretty decent argument for believing that his calculation is not robust as a calculation of the density matrix, rho R of the radiation, and that's just this density matrix is incredibly big. It's a d by d dimensional matrix, where d is the dimension of the Hilbert space. So at that time, it's basically a d A horizon over 4G times d A horizon over 4G matrix. And the thing about very, very large matrices is that very small changes in each of the elements can completely change the properties of the matrix of the quantum state. So in particular, just give you a simple example. If I have the matrix 1 over d, 1 over d, 1 over d, ... 0 everywhere else, that describes a maximally mixed state, the highest entropy it can possibly have. But I could, for example, change each of these matrix elements by an exponentially small amount, namely 1 over d, put 1 over d here, and here, and here, so on, so that now all the elements are equal to 1 over d. And that now describes the pure state that just looks like sum over I, 1 over square root d, ket I, times the corresponding bra. Okay, So that each of the elements of these two states only differ by order 1 over d, and yet they're completely different states. In this case, we could easily distinguish this state from the maximally mixed state by doing a measurement in the complementary basis, and we'd find that it has very different expectation on a simple operator. But for more complicated states, there's not a way to simply diagnose a pure state from a mixed state. So, okay, let's say we do believe Hawking's wrong. Then we'd like to have some idea, what the right answer should be, what the correct thing is. So to do that, we need a more explicit model of what we think should be happening if everything is unitary, that will let us at least make a guess for what the right answer should be if Hawking's not actually correct. That's what Don Page did in 1993. And it was a very simple idea that goes as follows. We don't know what the dynamics of the black hole are, so let's just make a completely blind guess. And by a blind guess, I mean, let's describe them by some unitary u that is chosen completely at random according to the Hart measure. Okay, so this is a stupid model, but it turns out for simple calculations, it can be a pretty good model of any sufficiently complex Hamiltonian, not like a free theory or something like that. Okay, so this unitary u acts on all the qubits describing this system B, describing the Hilbert space of the black hole. Okay, and then at some point, a Hawking quanta gets emitted. So we call this R, and the rest of them are still in B. And then maybe we have some more dynamics here, and then another quanta gets emitted, and so on. In fact, because this unitary is completely random, then if we add another random unitary here, then we still have the same random unitary we had before. So we can instead just think of we have all the dynamics at the beginning, and then just one by one, these qubits are spat out from B into R. Okay? So this is a manifestly unitary system. It's manifestly always going to be in a form like this, and we can try to compute S of R. So I'm not going to do this calculation for us. It's closely related to the calculation we'll get to on Wednesday, where we do the same thing in gravity. But the basic idea is that typical unitaries always maximize entanglement. If you start from this principle, you can get all the calculations right without ever doing any calculation at all in anger. So what do I mean by this? I mean we have two bounds here. Okay, SR can't be bigger than the number of qubits in R. And we also know that because SR is equal to SB for a pure state, then it also has to be less than the number of qubits in B. Okay, so it turns out that for typical unitaries, one of these two bounds is always saturated, whichever is smaller, and we have that SR is just equal to the min of NR and MB. Okay, so this, let me write this somewhere else a bit more prominent because it's important. The entropy of the Hawking radiation is just given by the smaller, the number of qubits of radiation, or the number of qubits of the black hole. This is the famous Page curve. In gravity, this NR here, number of qubits of R, is morally this thing I called S-rad, that is Hawking's calculation for the thermal entropy of the Hawking radiation, and this MB is just A horizon over 4G. So for gravity, this becomes SR, it's given by the min of Hawking's answer, and A horizon over 4G. The nice thing about this calculation is that it says, the reason it's implausible as a model, or one of them, is that it says that Hawking's calculation is right for as long as possible. And in particular, it's only when we have this really, really, really giant density matrix that Hawking's calculation is going to start going wrong, and we're going to have the entropy start going back down instead of continuing to go up. So this, if we expect that there could potentially be problems in Hawking's calculation at this point, and this is putting the problems, suggesting that the problems show up as late as possible, consistent with unitarity. Okay.
What are the main ideas that go into Page's argument? What assumptions are made about this quantum system?
So the technical statement of the calculation is that this unitary is drawn from what's called the Haar ensemble. Okay, so it's the Haar ensemble is the unique measure du, such that if I conjugate my unitaries by some u prime, then I have d u equals du prime u. The measure is left invariant under the action of the unitary group. And then that's all the assumptions we need, right? The only other input is the size of the input Hilbert space. We want that to be large. So there's actually, if you do the calculation very carefully, there's corrections to this when nr and nb are almost exactly the same size. It's actually a half qubit correction when they're exactly equal in size. But those exponentially, in general, the corrections are order 2 to the minus nb over nr, or vice versa, whichever gives a positive number. If nb is bigger than nr, then it's 2 to the minus. Sorry, this should be. Whoops. There's the dimensions. 2 to the minus nb plus nr. It's the difference in the number of qubits. So if I have, say, 10 more qubits in the black hole than in the radiation, or vice versa, then the size of the correction is 2 to the minus 10. So really, really, really small, very quickly. Yes, this is a very robust calculation. As I say, this calculation can be done in a way that's very closely analogous to the way we'll see how to do it in gravity on Wednesday. So I don't want to spend too much time going through the details. Okay, any other questions, by the way, about that? Please shout. Probably more useful you asking questions than me just talking, because it's more accurate to what you want to know. Okay, cool. So I would say if this is all we had, then there wouldn't be much of an information problem, because I think this argument, these big matrices, the calculation that Hawking did is not under control, is a very good one. We really shouldn't expect to be under control. But the problem is that we can make much more precise arguments about why there's a problem. And the first one I'm going to give is an argument by Lenny Susskind, I believe. Made it first back in the day. So, everything I've said so far, well, the page curve was early 90s. I think we're now going back further to 80s again. Certainly I haven't said anything that's 21st century. It's an argument from the no-cloning theorem. So what does the no-cloning theorem say? It's a very simple statement about the linearity of quantum mechanics. It says there's no linear map that takes all states of, say, a qubit, but it could be something larger, all states psi to psi tensor with psi, or more generally, psi tensor with, say, some unitary acting on psi. Okay? Why is this true? I can prove it in 2 lines for you. So let's say this was true. I'm going to prove by contradiction. Then 0 goes to 0, 0. 1 has to go to 1, 1. And the plus state, 1 over square root 2, 0 plus 1, has to go to a half, 0 plus 1, 0 plus 1. But 1 over square root 2 times this, plus 1 over square root 2 times this, minus this is equal to 0. On the other hand, you do the same thing with the right-hand side, and you get something not equal to 0, because there's terms of the form ket 0, ket 1 here, and there aren't any such terms over here. Okay? So, by linearity, then this map is impossible. Okay, so why is this relevant for black holes? Well, let's say we believe that Hawking's calculation just doesn't really work, and that actually at late times there's subtle corrections to it, so that if we look at the state of all these qubits of radiation after the black hole is basically fully evaporated, then it should be given by, I'll make a fairly loose version of the argument here, some complicated unitary describing the black hole S matrix times the original state psi that described the state of the star that fell into the black hole. Okay? But we can take a Cauchy slice through this space-time, sort of goes all the way up here, right up into the corner, and then it comes back down, doesn't hit the singularity, it stays space-like everywhere. To do this, we maybe need to stop slightly before the black hole fully evaporates, but that can be dealt with. I'm just lazy to do it. And so we have a single Cauchy slice that contains all this Hawking radiation and also contains the star here. Usual rules of quantum field theory, at least, maybe not quantum gravity, as we'll discuss, say that if you have a space-like slice, then heuristically, the state of a full slice is a tensor product over the different stuff on the slice. So the full state is psi tensor u psi. But that's exactly what we just argued can't ever happen in quantum mechanics because it can't be linear in the state psi of the star. Okay? So Lenny had an argument for why this wasn't a problem, which is called black hole complementarity. And I think it's clear at this point that in its original form, black hole complementarity doesn't really work. Or the original vision of why it was meant to work is wrong, even if the basic statements are right. But his idea was, okay, technically, if you try to describe the state on the whole slice at once, then it seems very problematic. It can't be done because it has to be nonlinear. But if a tree falls in a forest, according to Lenny Susskind, if no one hears it, then it doesn't make a sound. So what he said was, okay, that's already well, but if I want to see the state of the star down here after it fell in, so that it's actually space-like separated from this stuff, so there'd be no cloning paradox if it was the same state down here and up here because they're time-like separated, then I need to jump into the black hole. So I could be person A, call it Alice, jumps into the black hole, measures the state of the star, verifies that it's equal to psi, blah, blah, blah. Bob, meanwhile, could sit out at infinity. This is Bob. And Bob can collect up all the Hawking radiation as he goes, and he can do some terribly clever measurements of it that recover the state psi. And now Alice is sitting in the black hole with her state psi, and Bob has a copy of state psi out at infinity. But they're not able to talk to each other. Alice dies. Bob survives. He declares victory. He got the better deal in when they were assigning grad students to different experimental tasks. Then Bob probably got the more fun one than Alice. Yeah, so there's no problem because nobody ever observes the problem. So this is a good argument, but if we want to make it precise, then we need to know how long Bob has to wait in order to recover the information that fell into the star, okay, the contained in the star that fell in the black hole. Because if he doesn't have to wait terribly long, then maybe Bob can collect up a bit of radiation and then jump in. Meanwhile, Alice can look over here, but then try to accelerate out towards the edge of the black hole. And just before they reach the singularity, then they can meet up, compare notes, and go, what the hell, I guess the laws of the universe are really, really weird. And then they die sad because the physics didn't work the way they thought it did, or the no cloning theorem is false. It would be a sad way to end. Okay, so let's try to answer the question of how long we should expect Bob to have to wait to be able to recover some information that fell into the black hole. And we're going to do this by just studying Page's simple model of a black hole as a random unitary and see what happens. Okay. So we have the state of the star down here. and maybe some extra qubits get added in some fixed state that describe the increase of entropy as it forms a black hole. The star is a smaller system than the black hole. Then we have some random unitary here, and then some qubits of radiation start being spat out. Okay? I already claimed to you that as long as the number of qubits of radiation is less than the number of qubits of the black hole, i.e. we're before the page time, then SR is equal to number of qubits in R. That tells you that up to a very small error, the density matrix rho R is just 1 over D, 1 over D, dot, dot, dot. It's the maximally mixed state. Okay? It's pretty clear that if you just have collect up these radiation qubits and you try to learn something about the state psi, then you can't learn anything at all because it's just in the maximally mixed state no matter what psi was. Okay? So the page time, before the page time you can't learn anything about the star. So great, Bob has to sit out here way too long to ever have a chance of meeting up with Alice. That's page time is 10 to the 70 years or something, whatever it might be. That's within 10 orders of magnitude or so. For an astrophysical black hole, there's no way that Bob's ever going to see it. Okay, but we could go a bit cleverer, start think harder about how to actually form a problem. And the way to do that is to imagine that the thing we're going to call a cloning paradox with isn't going to be the original star that formed the black hole. Let me just erase a load of this. It's going to be some object, normally called a diary, that fell into the black hole at some later time. Okay? And we're going to try and set things up so that we get a smaller gap between the diary falling in and it coming back out and Bob getting to decode it and create a cloning paradox as possible so that we could potentially have them meet up. So this is what Hayden and Preskel studied in a beautiful paper from 2007. And there are two different regimes. One is when the diary's thrown in before the page time. Okay? In that case, it's obvious, again, that you don't learn anything until the page time because the density matrix still looks maximally mixed. And so, everything's very boring. We already know how it works. Okay? The more interesting situation is if we wait until we already have most of the qubits are in the radiation, black hole is smaller than before, and then we throw the diary in. Okay? So up to some unitary on the radiation, so the state at that late time looks maximally mixed on B before we throw the diary in. So this is B, and it's maximally entangled with some state in the radiation. So this is R, and it's some state that maximally entangles B with R. Okay? Now, we're going to take our diary, which we'll just take as an extra system here, call it D. Okay? And then we're going to let that fall into the black hole. So they have some random unitary U describing dynamics. Call this V instead. And then we get some more qubits coming out. Okay? And what we want to know is how long we have to wait until we can learn something about the state of the diary. The easiest test of this is to imagine that the diary we threw in was itself maximally entangled with some other system, D prime. Okay? Because then the information in R prime and R, all the radiation, will let us learn the state of the diary D if for this maximally entangled state, R and R prime is sort of maximally entangled with D prime. Okay? If the sort of information about the diary has been carried out into R prime, then they'll be entangled with one another. If it hasn't, then they won't be, and they'll be uncorrelated with one another. Okay, so all we need to do to compute the entanglement between D prime and all the radiation, R and R prime, is to compute two entropies. The first is just the entropy of R and R prime on its own, and the second is the entropy of R and R prime along with that extra system D prime. Okay? If D prime is entangled with these things, then this one will be smaller than this one. In fact, the difference will be the number of qubits in D prime if they're maximally entangled. If they're uncorrelated, then the same will be true, but the opposite way around. Okay? Okay, so let's compute these things. And we're going to do that by the principle I described up here, which is that typical unitaries, this is a random unitary U, will always act to maximize entanglement, to make as much entanglement as possible. Okay. So let's think about what bounds we have on the entropy of R and R prime. Well, forget about this isometry V. Let's just imagine R is down here. We're just going to do the same thing of the entropy of R and R prime has to be smaller than both the number of qubits in R plus the number in R prime. And it has to be smaller than the number of qubits in D plus the number of qubits in D prime.
Hi,
Okay.
sorry, it looks there is a question in the chat.
Okay, yeah.
Yeah, can you?
Okay. The reason that behind the decreasing of entanglement entropy of Hawking radiation after the page time is that initially SRAD is minimum, therefore we have linear growth up to the page time, and after the page time, a horizon over 4G is minimum, which is decreasing with time, which produces the page curve. Is this true? Yes, that's a completely correct statement. So we have 2 pages. Yeah, so the SR is given by this formula. I didn't do a plot, but maybe I should have done with time. Okay, so we plot SR with evaporation. Then initially, SRAD is monotonically increasing with time. Goes up something like this. And then at some point, it becomes bigger than a horizon over 4G. And then it goes down until eventually this goes to 0 and it hits 0. Okay? So as a function of time, that's what the page curve looks like. Yep.
Two quick questions. One is, we keep assuming maximal entanglement because that's what Hawking's calculation shows, or because it's a technical convenience, or what? Because then a lot of things, we use that as a powerful tool. The other question is about the no cloning application. In the no cloning, we're saying the radiation is U times psi, where psi was the interior state, but actually some of the interior state is evaporated away, so the interior state is not what it was before. So is there even a contradiction with no cloning? Because you could assume that the stuff that came out isn't inside anyway now, and so you're done. So could you clarify those 2 points?
Okay, so the first question is why are we assuming maximal entanglement? So for in the Hawking calculation, yeah, we see, so really it's a thermal state rather than maximal entanglement. That's a simplification of the model. We're ignoring the fact that we're at finite temperature. But we see that, all the qubits of radiation are basically unentangled with one another, uncorrelated. So, that's a prediction from Hawking, but then also if we do this model where we just treat it as a random unitary, then that's exactly what we see, right? Why do we think that's a good model? It's because A, it agrees with Hawking's calculation at early times, and B, it agrees with sufficiently chaotic Hamiltonians basically at all times. If I have the proverbial lump of coal that has some pretty strongly correlated physics, but radiates energy, then you'll get something that's basically a page curve. So then the second question was about the no cloning argument I gave. So I'm not sure I understood the question precisely. So I think you were saying that the interior has, so if I look at a Cauchy slice here, yeah. Yeah. Yeah.
Less stuff in the interior. So you might imagine that when the radiation comes out, that the information that it brings out, whatever stuff it brings out, is no longer inside. In which case you don't have a no cloning problem because you haven't cloned the interior state. The interior state just changed as it would in a lump of coal. There isn't a problem
I'm not sure I agree that the interior state does change or that there's less stuff at late time. So if I pick some Cauchy slice that sort of goes to the star here, and then maybe it goes out to infinity here, okay? Or I could alternatively pick some Cauchy slice that starts exactly the same, has the star in the same part of the Cauchy slice, but then it goes up to a very late time and has all the Hawking radiation in it. Both those Cauchy slices are exactly the same on the part here, and so the star is the same state in both of them.
Okay.
So yeah, that's the way the argument works.
Sorry, another question? Your
Yep.
proof of the no cloning theorem showed you can't clone 2 states, but black holes just need to clone 1 state, it seems. Could you comment on that?
Sorry, so, well, if there was some dynamics that did this for all states of the star, then it would presumably clone all states, right? So
Black
if
holes
we
are formed
only
by...
consider one particular state of the star and the Hilbert space evolving, then there's no paradox. But let's consider, simultaneously all the state where the star is in psi 0, the state where the star starts in psi 1, and the state in the star starts in the superposition of the two. And consistency of those 3 would lead to a violation of no cloning, if it was true for all of them.
Right,
If we believe in these semi-classical dynamics, then it should be true for any state of the star.
Okay, thank you.
So I fully agree with what you said earlier, but I still have a sort of a dumb confusion, I think. So if you run the Cauchy slice to go up, as you pointed out, and then go back to spatial infinity, the mass measured at spatial infinity presumably stays what it was, right? Because it's in the same place.
Yep.
However, if I were to try to do some kind of local integral, then there's stuff inside, there's stuff outside. Could you clarify how that sorts itself out?
So on this slice, there's just not very much energy. Thing stays constant. On this, we have a load of energy coming out here. And so, that makes the area much smaller up here. But then we actually have a load of negative energy ingoing flux coming across the horizon all along here. So it's a slightly weird thing that far from the black hole, the outgoing modes carry positive energy and the ingoing modes have 0 energy because they're just in the vacuum. Near the horizon, the outgoing modes are just Windler, it's just the Minkowski vacuum state, right? The Windler modes are thermal, but it's still a Minkowski vacuum. So they carry 0 energy, and the ingoing modes that were in the Minkowski vacuum and now in a singular state from the point of view of they're sort of in the Windler vacuum, they actually carry negative energy. So this, in 2D, this can be computed very nicely just from the fact that the energy momentum tensor is conserved and the conformal anomaly. So the trace of TAA equals minus C over 12 times R. And d mu T mu nu equals 0. If you use the boundary conditions at R equals infinity, has a positive energy flux going out and 0 coming in. And then you continue it to the horizon, you'll find a negative energy flux going in and 0 coming out.
So that's all fine. But just going back to the original point, just trying to get this very, very clear. If you took those 2 slices, in the first slice, you basically found nothing outside, tons of stuff inside. So when you do a local integral, you're picking up all the positive energy there. And the other slice, you pick up a lot of positive energy, some negative energy to cancel some of that out, and then you pick up some positive energy again. But again, going back to this thing of should you then conclude that the interior state has remained psi, I guess you're saying that because you're going to allow the thing to trace the original Cauchy slice as closely as you can up to the horizon. Is that correct?
Yeah, exactly. So the 2 Cauchy slices coincide on this section. They just look exactly the same there. After that they diverge, but with the state of this section of the Cauchy slice should be same in both of them, and then the state of this section of this Cauchy slice is in should contain the information, and that's enough to get no cloning.
Okay, so here's the dying man grasping for straws kind of thing. So what if the information in the radiation is only the stuff that isn't on the coincident part of the Cauchy slice in the interior?
Well, if you have more entropy in the star than the black hole has at this point in time, then you definitely need to have some information about the star coming out, have already come out in the radiation, right?
Okay, I think that takes care of it.
I could have made much more precise versions of that argument, but if you have Hayden-Preskel, say, then you know exactly when the information in the diary comes out. It's after a scrambling time, as I'm about to say, it's very quick. Okay, so let's go back to this very rough and ready calculation of how long we have to wait until information comes out. Okay, so S of R and R prime is just given by the small of these 2 things. In particular, we have MB equal to NR. So let's just call that NR. And so it's given by this one if the number of extra qubits that have come out up here it's bigger than the number of qubits that describe the diary. So if the diaries say 1 qubit, we only have to have 2 qubits come out in R prime for this thing to be smaller than this thing. Okay? What about if we do the same calculation for SR, R prime, D prime? It's now the minimum of NR plus NR prime plus N D prime, or just NB. Okay, because the two complementary systems are R prime and D prime and B itself. Okay, so again, that's equal to NR. So in this case, this one is always minimal. It's always NR. Okay? Great. So magically, if I believe this, then as long as NR prime is bigger than ND prime, so only after a handful of qubits have been emitted after the diary fell in, then I find that this one, the entropy of just R and R prime, is bigger than the entropy of R prime and D prime by exactly the number of qubits in D prime. That tells me D prime is maximally entangled with the Hawking radiation. It means that the information that fell in the diary have already got re-emitted in the radiation. Okay? Yep.
But will there be like nice factorization after the unitary? Like, will we be able to know, like, okay, this is B and this is R prime?
So R prime and R are far from the black hole, their radiation. So we ought to be able to, you know, in exact quantum gravity, maybe they're not really factors, but for the same reason that when we have some like photons in a lab, we're able to treat them as a subsystem and compute their entropy in a meaningful way. Then if we have Hawking radiation photons that are like, you know, 100 times the Schwarzschild radius from the black hole, we ought to be able to treat them as a subsystem to a very high precision. So
Okay.
maybe I misunderstood the question.
No, I think the answer is just to make sure. So when you do your when you make the claim that NB equal to NR at some point it's the same. This really has to just do with
the claim that NB equals to NR is slightly sloppy. So really what I had before was some isometry. So the number of radiation qubits, we were well after the page time, was actually much larger than NB. Okay? But we already knew that the early radiation was maximally entangled with B. That was the page curve computation. Okay? So the number of like relevant qubits, we could imagine that we distilled out some set of qubits from the early radiation that is already maximally entangled with B. And you know, we get some stuff that are uncorrelated with B, and that will stay uncorrelated, and we can just throw it away. Okay. So that's the sense in which it's the relevant number of degrees of freedom in the early radiation is the same number as MB, because that's the entanglement energy.
Super. Thank you.
Yeah. Yep.
Hi, so I may have misunderstood, but it looks like SR prime is always larger than SR prime D prime, right? For whatever ND prime and NR prime are. Because the bottom line is just NR, and the upper line is NR plus some positive number?
Yes, yes. So this one is always limited by NR.
So it seems independent of the amount of radiation that goes outside, the NR prime, I mean.
No, sorry.
So
Yeah. Sorry. That's a good point, and that's me screwing up my identifications. The claim is that, good. NB plus NR, NB is decreasing. So the actual claim is NR plus ND equals NB plus NR prime. Okay, because these are the inputs to the unitary and these are the outputs to the unitary. And so then if I did that right there, I would still have the same claim. Great. Sorry about that. I apologize for that very embarrassing error. Okay, great. The takeaway, as I say, is that we only seemingly need to wait for a couple of qubits to be emitted, and then we already learn what was in the diary. But there's a big subtlety here, which is that we assumed this had actually fallen into the black hole and had enough time to interact with the rest of the stuff in the black hole that we could treat this as a random unitary. Okay? So this time for a couple of qubits to be emitted is order R Schwarzschild. But the time even for the Hawking quanta to sort of fall in from a decent distance away to the horizon and get close to the horizon, which we'd like to say is at least a lower bound, is quite a lot longer than our Schwarzschild. And then for some information to get back out. So Hayden and Presko actually made an inspired guess that the time for this to happen is order log the entropy of the black hole, log the horizon area over 4G, times our Schwarzschild. And at the time, they didn't have much justification for that beyond it was sort of the fastest plausible time that could be true if you had sufficiently strongly coupled but k-local dynamics. But now we have very precise computations in ADS-CFT. So what this is it's the timescale for the black hole to what's called scramble, to all the degrees of freedom to get fully mixed up, okay? Once that's happened, we can model it well by a random unitary. And there's a precise timescale it takes for this to happen. It's exactly beta over 2 pi log SBH. Okay, so actually that is the limiting factor in how long it takes for the information to get back out, not the time for then a few more qubits to be emitted, because that's only order beta. Okay, so this is the timescale we expect for a diode to be thrown in. Alice jumps in with it. And then for Bob to be able to collect up information that, along with the early radiation, is sufficient for him to decode the state. This timescale, by the way, is still incredibly fast. It's order of a second for astrophysical black holes. So if you're used to black hole evaporation always being about incredibly long timescale things, then this just fundamentally isn't. Except, of course, we had to wait until after the page time to be able to do it at all. And we had to use this huge amount of entanglement in order to be able to recover the information and so on. But it is a short timescale. But it turns out it's almost, but not quite, really fast enough for Bob to be able to jump in and compare notes and try to get a no-cloning paradox. So you can try to do the calculation, and Hayden and Presko concluded that it was impossible and it was all safe. It really is actually pretty borderline. It's like requires sort of Planck scale energies, but not much greater than, parametrically greater than Planck scale energies. But it's enough that you can say, okay, complementarity is still fine. You still can't see any no cloning, blah, blah, blah. Everything works out. Unfortunately, the last 15 minutes, I'm going to give you an argument that really does, I think, put the nail in the coffin of black hole complementarity can always save you. You can never see a no cloning argument. And that is, go for this blackboard. That is the AMP's firewall argument. So it's actually almost the same argument as the Hayden and Presko argument. It just, because of the exact setup they're using, it basically makes it obvious that it can be seen. So let's see how that works. Okay. So what do AMPs say? They say let's not bother throwing anything in at all. Okay? All we're going to do is we're going to use the fact that there's already stuff in there, which is, it's the interior partners of Hawking modes. Okay, so we're going to have some late time Hawking mode, and there's some interior partner at that mode. Okay. We also have all this early radiation. So I'll call this conventional letters for these things. Early radiation, call E. This I'll call L. This I'll call L prime. Okay? So, the statement of the page curve is that SLE is equal to the entropy of E minus the number of qubits in L. Okay, we're ignoring finite temperature stuff and so on, but in the toy model, then that's exactly the case. So this means necessarily that L is maximally entangled with E. Okay? Someone out here can therefore, in principle, find some unitary, acts on the state, some complicated state, psi LE, some unitary acting on E that takes this to the state 0 E prime L plus 1, a bell pair maximally entangling L with some subsystem of E, tensored with some other state on I'll call it E bar, the remaining subsystem of E other than E prime. Okay, that's something I can always do if I have a maximally entangled state. I'm just distilling out the entanglement into an entangled pair of 2 qubits. Okay, so let's say Bob does that. We'll ignore the process of doing that, though it's important. In fact, this unitary is generically exponentially complicated, so the time that would be required to do that is vastly longer than the time that the black hole would evaporate. Nonetheless, we will pretend that Bob is magically able to do that, and he then has some qubit E prime that is maximally entangled with this qubit L. Okay? He then jumps in, carrying that qubit E prime. As he passes L, he collects L as he goes along. Again, there's issues with doing that because L is delocalized across the whole horizon. But I don't think those issues are super problematic. You can imagine a team getting together and trying to collect it all up before the black hole, and they can normally sort of pull it off in certain circumstances, certain dimensions, so on. So we'll assume that they can. Okay, so he's now crossing the black hole horizon with a qubit L and a qubit E that are maximally entangled with one another. Now he hits L prime, and he collects that up too. Okay, so now he has 3 qubits. E, L, and L prime. And the claim of the page curve is that E prime is maximally entangled with L. So S of E prime and L is equal to 0. S of E equals S of L equals 1. But the claim of semi-classical Hawking evaporation is that L is maximally entangled with L prime. L prime equals 0. S of L equals S of L prime equals 1. Okay, but there is a statement of some strong subadditivity that S of E L L prime, S of L L prime plus S of E prime L is greater than or equal to S of L plus S of L E prime L prime. Okay, this is just a statement true about any quantum states. And we see that if these two are both equal to 0 and this is equal to 1, then we have a paradox. That is the AMS paradox. Important points about it are 1, that once Bob is jumping in, these are only involving small dimensional systems, so the arguments that Hawking's calculation for the entropy is not robust because it's involving some huge Hilbert space do not apply. Like if we know the state to know density matrix elements of L and E L prime to like order 1 precision, we know the entropies to order 1 precision. It's also robust to, it's not like if we make change this state slightly, then this entropy might become slightly non-zero. This one might become slightly non-zero. This one might become slightly less than 1, but you're still clearly violating the inequality. So you can't just have some approximations save you. And theoretically, as long as we assume Bob can do this exponentially complex process before he jumps in, then all 3 things can be seen by 1 observer at 1 point in space-time. Okay, so this is really a paradox. The only way to resolve all this would have quantum mechanics just not be true in Bob's lab, just sitting inside the horizon as he falls in. Yep.
Yeah, I was gonna read it. Yeah, they're asking where is E prime in the Penrose diagram?
Yeah, good. So E was all the early radiation. Okay. So the claim with the page curve is that some degree of freedom in that early radiation that will in general be very delocalized and very, very complicated is maximally entangled with L. Okay, this just followed from the fact that the entropy of L in E was equal to the entropy of E minus the number of qubits in L. Okay, so it's not some simple quanta somewhere on the Penrose diagram, but it's just it's a subsystem of this whole quantum system E. Okay, that Bob can collect up on his timeline down here before he jumps in. The trouble, of course, is that he has to distill that small subsystem out, because otherwise he'd have to jump in with something with a mass larger than the black hole, and then he wouldn't be able to fit inside the black hole. And that distillation process is hard. Yep.
Is there ever an issue with identifying E prime? Like, if I'm an observer, I have to pick this qubit, and then I have to also know the qubit that I'm going to see at the horizon?
Yeah, so the idea is that the idea is that Bob is better than us at quantum gravity, and so he knows the black hole S matrix, and so he's exactly able to identify that qubit. Of course, even if you know an in-principle formulation of the black hole S matrix, you probably can't calculate what you should be doing. And even if you can calculate what you should be doing, then you can't actually do it because it's some impossibly complex quantum computation to do. There are algorithms that would do this for you if you have the ability to simulate a black hole in your lab in a precise way, which, if the fundamental microscopic dynamics, if you understand them, then you should be able to do that. But they will take an exponential time. So that is not like the Hayden-Preskel thing where it's like, maybe they can see each other, but maybe they can't. Let's hope they can't because it saves us. That's like, it's unimaginably vastly longer timescales than anything involving evaporation in black holes. E to the 10 to the 70 years rather than 10 to the 70 years. That's a pretty big difference. Yeah. Any other questions? Doesn't SSA assume Hilbert space factorization? Should we assume it here in a theory of quantum gravity? Again, in the full theory of quantum gravity, then the Hilbert space structure is probably very, very complicated. But E, L, and L prime, E prime, L, and L prime are still small quantum systems, like qubits, that have been distilled out and are stored in Bob's lab. Okay? And if quantum gravity stops us from treating just like quantum subsystems in a lab as factorizing separate subsystems, then we're in trouble because all the AMO people and the condensed matter people and so on are going to really want to know that because they want to know that all the experiments they're doing are total nonsense and aren't meant to work, and we can't do any physics. So I don't think issues with the fundamental degrees of freedom of quantum gravity should be able to affect whether that effective description in terms of a few subsystems of small quantum systems works, because if it did, then it would destroy our ability to do physics and ignore gravity in the everyday world. Yeah.
I've not been a bit too careful, like following the assumptions and everything that led to this argument, but is this also valid for like ADS2 JT gravity sort of picture where we kind of know like the dynamics too well that maybe we could actually compute these things?
Yes. So in JT gravity, you can with matter, say you can certainly do this. You can. Yes. So if you want to have a page curve, then so there's two. If you just have so-called just the disk JT gravity, then that's basically S naught equals infinity, where S naught is the term in front of the Einstein-Hilbert action. So then you'll never hit the page time. But if you're doing JT gravity, including the effects of higher topologies, i.e. finite S naught, then yeah, you should be able to hit the page time. And after the page time, you have this paradox. And as I'll discuss on Wednesday, then there's calculations you can do that would say, roughly, or they seem to want to tell us that when you do this complicated process that extracts E prime out of E, what you end up doing in the semi-classical description is you extract L prime out of the interior. And so then you jump into the interior and you find that L prime is no longer there because you did some very complicated thing that broke semi-classical causality and extracted it out. Now that's an interpretation of some calculations that hopefully I'll have time to talk about on Wednesday. But yeah, that's the so-called A equals RB proposal for resolving the firewall paradox, or ER equals EPR sometimes. that, we just accept that this L prime really is the same degree of freedom as the complicated operator on E. And so if we distill that out and start carrying it with us, then L prime is no longer there because we did something that had a non-local effect on the semi-classical spacetime and extracted out L prime.
Does this relate to, I'm still here, does this relate to the fact that you have to add additional topologies like some trumpet geometry?
Yeah, so the calculations that show it being extracted out are analytic continuations of topologies where there's a wormhole and L prime goes out through the wormhole and
Okay.
That's why it's no longer there. Yeah.
Okay, thank you.
Okay. Yeah, I think that's pretty much what I had to say. So yeah, tomorrow we're going to switch tacks. As I say, we're going to talk about ADS-CFT, going to talk about Ryutake Nagi, its generalizations, where they work, where they don't work, how to derive them. In particular, we'll spend quite a bit of time on the Lukowitz-Maldacena argument for deriving RT, because I think that's arguably the most insightful and important idea in the last 10 years of quantum gravity. And yeah, also the paper isn't the easiest to learn from, so possibly you can extract out the most important information in a talk better. And then on Wednesday we'll bring everything together and we'll see how those ideas can be used to resolve some, but maybe not all of the questions about how the black hole information problem works. So yeah, cool, awesome. See you guys tomorrow.